Hello all, I hope you're all healthy, safe and home. Welcome to our new lecture, Concepts, and this actually is our last C lecture, okay? And I will start by a recap and some tracing with pointers to make sure we are all on the same page and you don't have a problem with it before we move on, okay? Last time we already took a look at how the C programs that we write are executed, and there is just one point that you might read about, okay, which is the preprocessor, okay, and from the name, the preprocessor is actually responsible for pre-processing the file. So sometimes in C, okay, you will find that we define a constant value, okay. So I can, for example, okay, go and define, for example, pi 3.14. Okay, this would mean that I have a constant value called pi, and the value of it is 3.14. So throughout my file, I can actually use pi. Okay, so in this case, what the preprocessor will do is it will take your file and it will sort of understand the meaning of this line, which is that you're defining a constant value that you're naming pi, and it sort of replaces, for example, every occurrence of the identifier pi with the value of it. Okay, and it also handles the comments, for example. Okay, which will not be part of what actually will be executed. So it should not be part of the assembly code and then the machine code that is produced. Okay, so let's move on to an example of scanning. Okay, we didn't do a lot of that last time. As you can see here, whenever we scan, we actually write here the address of the variable in which we want to save. Okay, so basically we will scan and save into this address. Okay, if I don't know the address, which is always the case, I would never know if I just write int x where the x is saved inside the memory. So we use the AND in order to get the address. So this is something that is built into C. It's a utility that C provides us. Okay, so let's see an example. If you remember this last time, we had an example in which we saw the conditions if, how do we write ifs, and in this case we wanted to get the maximum, or to know the maximum among three integers x, y, and z. Okay, so if you just compile and run this, you would get that z is the maximum, which is correct. Okay, now what I want to do is, instead of having these written, I want to actually have them from the user. Okay, so I just declare that I have three variables, x, y, and z, and I start to scan. Okay, so let's do it one by one. Let's scan for the x first. Okay, the thing is, if you just write scan, and I'm scanning a decimal, and in this case I will save it into the x, so I have to write the address of x, which is and x. Okay, I will not get, when I compile and I run, I don't get a message. Okay, so if I write 6, then it will scan and it will run normally, and in this case the z is still the maximum. If I run again, and in this case I enter 600, okay, I get x is the maximum, which is basically what should be the maximum in this example. Okay, so what I want to do is, before this, I want to print something that would be sort of representative of what the user should enter. So in this case, I will write a print statement, and this is why usually this is what you will see. We write a print and then we ask the user, please enter a value for x, and we just scan. So in this case, if I compile, and I have to have the semicolon, if I compile and I run, I get the descriptive message. So in this case, I enter 12, okay, and z is the maximum. Okay, so I will do the same for the y, and in this case it will be the y, and I will save into the y, and I do the same for the z, and I save into the z. So in this case, if I compile and I run, I enter for the x 50, for the y 90, and for the z negative 5. The y is the maximum, which is correct. Okay, so in the tutorials you've also seen, or in the tutorial you've seen the difference between the percentage D and the percentage I in the scanning. Okay, it has to do with the different formats of the numbers that you can accept. For me, within the scope of the examples I will run with you, I will always scan for a decimal, and I use the percentage D always. Okay. So last time we took a look at the if then else conditional statement, and it basically looks the same like in Java. And as we said, whenever in this case we will be using the braces, because this is a question that we got in the interactive tool. Throughout the chat, we got the question whether we use the indentation like Python or not. So the answer is no, we don't use indentation to define the block of statements. The block of statements is defined using the braces. So basically, if you have only one statement inside your block, you do not have to use the braces. And if you have more than one statement, then you have to use the braces. Okay, so why do we indent in the code and in the examples that we've seen last time and this time? For readability. This is the convention. So usually this is what we do in any language. Okay, so in this case, if you go back to the example, you will find that we actually did not use braces, because in this case the then part has only one, in this case, statement. Okay, now another option of in this case conditional statements is a switch statement. Okay, and you already of course know that from Java. So in this case the syntax is similar. You switch on a variable name or an expression, and then what you have here is the different cases for the values that this expression or variable would have. Okay, so in case it matches this value, this is what happens. Okay, and then you have to break. Okay, in case it matches this, this is what happens, and in case it doesn't match any, then you go for the default. So let's go for an example, and in this case what we want to do is we want to have two scores. The scores can come from the user, or they can be just for now values that we will enter. Okay, so I have two scores, 1 and 2, and then I want to check whether player 1 won or not, and a player can only win if their score is exactly equal to 100. So what I will do is I will switch on score 1. Okay, and then I have to check what are the values that I'm interested to check. In this case, the only value is actually 100, so I will say case 100, and then in this case what will happen is I can print, for example, player 1 wins, and then I have another statement, game over. Okay, now if this is not the case, okay, then I will go for the default case, and in this case what I can do is I can print the following. I can print, for example, that as a start player 1 did not win, and I know for sure that player 1 did not win. Okay, now let's try this, and let's set the score of player 1 to be 100. Now if you try, I will compile, I will run, and this is what I get. Player 1 wins, game over. Player 1 did not win. Okay, so why did I get both? I can just add the new lines. Why did I get both? That player 1 wins and then player 1 did not win. Because as you can see here, what we did is we did not break. Okay, so after they check, or after C checks that the score is 100, and then it executes this and then that, it will not stop. It will move on, and it will execute this as well. Okay, so this is not what I want to do. I want to make sure that if I match a case and I execute it, I do not do any other cases. So I have to break the switch. Okay, so in this case, the only case that I will go into the default is if the score of player 1 is actually not 100. So as you can see here, if the score is 100, I get player 1 wins, game over. and if the score is not 100, if it's 80 for example, then I get player 1 did not win, which is exactly what I want to have. Okay, what you can do here is you can check whether player 2 won or not. Of course, this could be done with a if statement. Okay, in this case it will be just a check if the score is equal to 100. So in this case the cases could be more intuitive and easy to use when you have a lot of cases and you don't want to nest a lot of if then else. Okay, so in this case it will be easy if you have a specific expression or a specific value that you're checking for. So what do I mean by an expression? So in this case, instead of switching over or according to the value of score 1, you can switch over the value of score 1 plus 20. So in this case, as you can see, what you will be switching over will be 80 plus 20, which is 100. So this will match that, and you get that player 1 wins and game over. Okay, so what you need to have here is something that evaluates to a value, and these are the values that you'll be checking throughout the cases. Okay, now for the iterative statements, we can have the while loop, which you already know, and we did take a look at a for loop last time. Okay, and we also have a do while. Okay, what's the difference between a while and the do while? The do while does the loop at least one time. However, the while can do the loop 0 times if the condition fails from the beginning. Okay, but the do while checks the condition after the blocks are executed once. Okay, now let's do a couple of tracing with pointers before we move on, because today we will need pointers as well. So grab please a piece of paper, okay, and try to trace this, and I'll do it with you. Okay, so while I'm drawing, you can also try to do the same. You can draw and we can see what we have. So in this case, I will assume we have our memory, and in our memory you have some variables. So I have the A, and I don't know where it is. I'll just randomly put them anywhere. So I have the A. I have another variable, okay, which is the Y. Now, if I ask you what is the data type of the A, you will tell me that A is an integer. But if I ask you what is the data type of the Y, you will tell me Y is now not an integer, because if it was an integer, it would have looked like the A without this asterisk. So the existence of this asterisk means that it has a special data type, and this special data type is the pointer data type. Now, the pointer data type, okay, in this case means that the variables of this type will have values that are addresses. Okay, so Y is basically a variable, and the value of the Y has to be an address. Okay, now what is the address that I will put here? I don't know. I don't have a value for the Y yet, similar to the A, which I don't have a value for it yet. So it's declared, but it's uninitialized yet, or it doesn't have a value yet. So in this case, okay, what I want you to know is the data type that we write here actually differs. So I can have an integer pointer and I can have a char pointer. I can have something like this, CP for example. So CP is still a pointer because you have this asterisk. However, it's a pointer to a char. However, the Y is a pointer to an integer. What does this mean? The value of the Y is an address, okay? The address, okay, has to be an address in the memory, and this address has to contain inside it something of the type int. Now for the CP is still a pointer, so it's still an address. So it will hold an address, okay, and it will be an address of a place inside the memory, and this place has to contain a char, okay? So let's move on. This is not part of the code. So what did we do next? We have another pointer x. However, here we have a value for it. What's the value of it? And A. We just used the and with the scanning a bit ago. And in this case, what we said is that the and A means that this is the address of A. So I'll just write address of A. Okay, let me try to do it. And usually, just for a better visualization, a pointer is actually represented visually with an arrow, okay? So in this case, I have something pointing to the A, okay? And this thing is actually the X, okay? So it is still a variable inside the memory, however, it's a pointer. So we usually also represent it with this format, Okay, now what did we do next? Okay, what we did next is we started to manipulate a value from the memory using the x. So now the x is a variable. What is the value of the variable? It's an address, and in this case it's the address of a, which is an integer, and this is correct because actually x is an integer pointer. Now take a look at this thing. Asterisk x equals 15. Now asterisk x in this case, okay, is an operation done on the x. So in this case, this asterisk is used to declare a variable x of a specific data type. But once the variable is declared, using the asterisk with it means that you're applying an operation. Now, what is the operation that you're applying? In this case, it's not a multiplication. In this case, you're applying it on a pointer, on the x, which is a pointer. And this is what we call dereferencing the pointer. What does this mean? Now, in this case, this is a dereferencing, in this case, operation applied on x. What does dereferencing do? It gets the value inside this address. So, x points here. The value of x is this address. It points inside this location. What's inside this location? This is what we get once we dereference the x. Now, you can have it on both hand sides. So you can say asterisk x equals whatever. Okay, so in this case, 10, for example. So in this case, I will go and whatever the x is accessing, I will change its value to become 10. Or I can do it the other way around. I can say, for example, let's assume I have int b equals 19, and then I say b is equal to asterisk x. So in this case, what do I do? Instead of writing into it, I will read it. It's on the right hand side of the equal. Okay, so I will access it, get the value that the x is pointing to, and assign this value to b. Okay, so let's take a look at what we do here. In this case, I dereference x, but it's on the left hand side. So it's as if I will assign to the location that x is pointing to a value. What's the value that I'm assigning? It's the value 15. So now the value that the x is pointing to is 15. Now, this value is actually the a. So it's as if you changed the value of a, but without doing it through the a, you did it through the address of a, which is x. The second thing you do is this. Now this, if you write it, it's as if you're saying asterisk x is equal to asterisk x plus 2. So I will do it on two steps. First of all, I will get the right hand side. The right hand side is basically asterisk x, which is the value that x is pointing to, which is 15. So in this case, this is 15, okay? And I add to it 2, okay? So in this case, what do I get? I get 15, which is the value of asterisk x plus 2. So in this case, I have 17. So it's as if you will write this asterisk x is equal to 17. Okay, so this is basically what we end up having. Asterisk x is equal to 17. So now what do we do? Asterisk x, whatever x is pointing to, will now have another value, and this value, instead of it being 15, it will now become another value, which is 17. So now I rechanged the value of the a, but instead of doing it through the a, I did it through the pointer, which is x. Now what do I do? Y is another pointer. Okay, do I have a value for it? No. Now I will assign to the value of y a value which is the address of a. Why? Because y is equal to x. What's the value of x? The value of x is address a. So the value of y will become the same as the value of x, which is address a. And in this case, similarly, it is a pointer, so I will do it the same way. It is a pointer, so I will do it with a arrow, and in this case it's a y. Okay, so in this case I have the x and the y pointing to the same location. Why? Because both have the same value, address of a. Okay, now what do? I do this statement. Asterisk y times equal, okay, 2, which means asterisk y equals asterisk y plus 2. So similarly, I will start with the right hand side. Asterisk y alone is whatever the y is pointing to, which is 17. 17 plus 2 is, in this case, I'm sorry, it's not a plus, it's times. 17 times 2, in this case, will become a new value, which is, in this case, 17. times 2, which is a new value, which is the 34. So it's as if here I will replace the value that the y is pointing to become a new value, which in this case is 34. So again, it is as if you changed the value of a without doing it directly. How did you do it? You did it through the pointers. Now let's go and trace it on C. Let's actually run it, okay? So I'll just copy the code and I'll add a couple of print statements so that we trace. So this is exactly the code that we had, and I added some prints. Okay, let's do it one by one. So in this case, I just print the value of a, and as we saw from our tracing, the value of a will become 34. Okay, now if I go and I decide to print asterisk x asterisk y, what does this mean? This means that I will go to the x and dereference it, which means I get the value inside this location and the value inside the location y. Okay, both x and y point to a. So if you dereference x and if you dereference y, you get the same value as the value of a, which is also the 34. Okay, now take a look at the last two print statements. In this case, what am I printing? I'm actually printing the value of x and the value of y. My question is, what type is the x and the y? They are actually pointers. So in this case, their values are memory addresses, and this is why I have percentage p, which means I'm printing a pointer. Now, my question is, x and y, will they have the same value or different values? They will have the same value, and their value is actually equal to the address of a. Okay, so in this case the value will look weird because it's an address, but as you can see, both of them have the same exact value, which is the address of a. My question now is, the address of x and the address of y, are they the same or different? And the answer is, of course, they're different, because they are two different, in this case, two different variables, which mean that each variable is saved in a different location inside the memory. So each one of them will have a different location. Okay, so let me add here another line so that it's clearer. So as you can see, the and x, which is the address of x, has a value that is different from the and y, which is the address of y. Okay, so this was our first example. One last thing about this example, if I decide to print the address of a, it will be exactly the same as the value of x and as the value of y, because x and y are actually both initialized, or they have the value of and a, which is the address of a. So if you decide to print and a, you get exactly what you get for the value of x and y. These three prints will be exactly the same, which is the address of a. Now this is our second example, and this I think was the last slide of the previous lecture. So I just started out to save some time. I just drew the memory, okay, or some of the memory, and I started the initialization part. So in this case I have int a equals 10, so I have a and it has a value 10, and we have another integer b with a value 10. And then we have two other integers c and d, but they don't have values yet. And then we have this, and you now know that once you see this, you know that this actually is a special data type, and in this case, or this variable has a special data type, and you know that the value of this variable has to be an address. So this is an integer pointer, okay, ptr, and it's a variable at the end of the day. So you declare it with the variable name, which is ptra in this case, and the data type, which is an integer pointer, and the value in this case, which you initialize this variable with, is and a. And a is basically the address of a, and this is why here I've written address of a, okay? And we also symbolize it or visualize it with this arrow. Pointer a points to a, okay? And then you have another pointer, we call it pointer b in this case, and the value of it is the address of b. So ptrb has the value address of b, which means that it points to b. Now this is just these lines. Now we start there, okay? Plus plus asterisk ptra. Asterisk ptra alone, what does it mean? It means the dereferencing of pointer a, which means this value. Now, what will I do with it? will I just read it or will I change it? I will change it because the plus plus will change. So in this case, the new value will become the plus plus, which is basically 11. So let me write here the new value of A, which is 11. Okay, now asterisk PTRB and then all plus plus. Now here there is a difference. Like what we saw last time, if you assign that to a value, there will be a difference. But now for us, because we don't assign either of these, so in this case, we don't actually have a difference in the behavior in our example, because in this case, both, we just use them to increment, okay? Whether it's plus plus, a variable or a value plus plus, okay? So the difference will be if you assign that into another variable, and we've seen that last time. So asterisk PTRB, which is this, okay, you dereference the pointer, the value that the pointer is pointing to, and then plus plus, which means that it will also change to become 11. Okay, now at this point, what will you do? You will print. So let me write with you what will be printed, and in this case I have to write exactly what C will show. So C will first of all print a new line and then write A equals and then a value, okay, and this value is a decimal value and the value of it is A, so it will write A equals 11, followed by a space, comma, space, and then B equals and then a space and then another decimal, which in this case is 11 as well. Okay, so this is the first print. Now take a look at what we have here. Now here you will start to see the difference. As you can see here, this is plus plus something, and then here we have something plus plus. So plus plus something, we first of all increment and then we assign. So we will go and we increment this. What is this? This is asterisk PTRA, which means we increment whatever the PTRA is pointing to, which is this value. So basically I will go and I will increment this value, and then I will assign the new value, the incremented value, which is 12, to the C. So the C becomes 12. Okay, now this is the other way around. First of all, we assign the D to this value before the increment, which is asterisk PTRB, which is this value 11. So the D has the value 11, and then you go and you increment asterisk PTRB. So this becomes 12. Okay, now if you go to these two prints, okay, I will trace them. So in this case I print A is equal to 12 and then comma, B is equal to 12, and then we have in a new line C is equal to 12 comma, D is equal to 11. Okay, so this is the print that we have. Let's go to C and trace it. So if I go and I write it, I compile, I run, I get exactly what we wrote together. Okay, so this is another example, and in this example we've seen actually pointers in addition to the dereferencing, okay, because we got some questions about them in the live chat last time as well. Now this is another example, and we will start. We have int name, which is an array, and it has 3 elements, 5, 23, and 119. As we said last time, the variable that represents the array is actually a pointer to the first element of the array, and this is why name is actually a variable in which an address is saved. Which address is saved? The address of the first element of the array. And this is why I didn't write here address of whatever like in the previous examples. I will just show it by the pointer. Okay, and then we have int asterisk p asterisk q, which means that p and q are two also integer pointers, but we do not have values for them yet. Okay, and then p equals name, which means that the value assigned to p, so here I will assign some value to the p, okay, which will be an address as well, okay, which will be the same as whatever the name is pointing to. And this is why, just to make it easier, I will use in this example the arrows. So in this case I will have another arrow, and this arrow will be pointing also to the first address, the address of the, or pointing to the first element of the array. And this is why p will contain the address of the 5, or the address of the first element of the array. And then the q is equal to name plus 1. So now the name is a variable, and I'm applying the plus 1 to it. In this case, what will the plus 1 do? Now, in general, if you have an integer plus 1, so if you do 5 plus 1, the new value is 6. But if you do an address +1, this does not mean that you will change it by one value, okay? This means that you will actually be now pointing to the next address, okay? The difference between one address and the next address might depend, or actually it depends on the size of the word, okay? So it's not usually the case that we have 1, 2, 3. No, we might have 1, 5, okay? If the size of one word is, for example, 4, or we actually have 0, 4, 8, okay? And this is why the +1 does not mean that the difference will be 1 decimal, okay? The difference is the difference between two addresses in this setting, okay? So basically what we actually will do is the Q will be assigned to the next address. So the name points here and the P points to the same address. The Q will point to the next address, which is the address of the 23. I will do it on the other side just to save some space. So, oh, I need to do it this way. So let me try out. So, okay. So this is my Q, okay? So in this case, this is my Q. It points to the next address, and now the Q is no longer, or it has actually some value now, which is an address of the 23. Now, if you do the print at this point, what do? You are printing an integer followed by a space, followed by an integer, followed by a space, followed by an integer, space, and then new line. What are the three integers that you print? The first integer that you print is asterisk name. Name is a pointer. Asterisk name means you dereference the pointer. So you go to the pointer and you check what is it pointing to. What's the value? 5. Asterisk P. What is it? Also 5. Asterisk Q. What is it? 23. Okay. So now we have the first print. Let's move on. P plus plus. Okay. And then we dereference. Okay, so in this case, what are we dereferencing? Are we dereferencing only the P? No. If we were dereferencing the P, it would have been asterisk P. Okay, but this is not the case. It's actually P plus plus and then an asterisk. What does this mean? The P plus plus, what will it do? It will increment the P. So now the P, where will it point? It will point to the next address. Okay, so now what I have is the P actually points here. So this is P plus plus. And then dereferencing. Dereferencing the P plus plus. Okay. So I increment the P. It's now pointing here. So I'm done with this part. Okay. And then, so this part is done. And then I dereference. I dereference, but I don't do anything with the value that I dereference. So dereferencing will return the 23. But do I do anything with it? No. So I just don't do anything. Okay. Now we move on. Asterisk Q plus plus. Now this is different. Now asterisk Q means that you go and you dereference the Q, okay, which will get you the value 23. And then what do you do with this value? Plus plus. You increment it, which means that the new value here will become 24. Okay. So now we go and we execute the second print. In this case, I print an integer followed by space, followed by an integer and a new line. The first integer I print is asterisk P. Asterisk P in this case is the 24. Okay. And then Q of 0. Now, this might be for you a bit weird. Why? Because we never initialized an array named Q. However, at the end of the day, we said that whenever you initialize an array this way, this name, this variable is actually a pointer, okay, that points to the first address. And whenever you say name of 2, this means that you will be going to the third element. And by default, C will understand this. So also this will work the same way. Q of 0 means that Q is a pointer. And then how many displacements, how many places will you move from the Q? You will move 0 places. So basically, you also get the 24. Okay, so let's check what we actually get from C. So if we go to C and we check, we actually get exactly the same. We get 5, 5, 23. And then the next time we get 24, 24. Okay, so this is our third tracing example. Okay, and in this example, we linked the dereferencing with the pointers and the arrays. And all these concepts are concepts that are crucial for today. And this is why we started by them. Okay. Okay, so this is also something that you should always remember with C, passing by value and reference. Okay, and in this case, whenever you pass something, it's a copy is taken, and this is why if you pass the address and then you change using the dereferencing, then the change is actually reflected in memory, and this is why this swap works and this swap does not work. Now, take a look at this swap. Okay, and I want you to think whether it works or not. Okay, now in this case, what we have is we still have pointers. Okay, so I still initialize two pointers, P and Q, with the addresses of A and B. However, take a look at this swap. This swap actually takes as arguments two integers. Okay, and from here, I actually send the result of dereferencing P and dereferencing Q. So although I have two pointers, so the P and the Q do hold addresses, but what did I choose to send? Did I choose to send the address? No, I actually chose to send the value. Okay, so at the end of the day, this will behave exactly like this one. Okay, because at the end of the day, you're still sending a copy. You're still getting a value and sending a copy of the value. Here, you get a value and you send a copy of the value. It doesn't matter that you get the value through the pointer. At the end of the day, it is a value. Okay, so this is basically just a summary of everything we've done so far with the pointers. The most important things we've covered a lot today is the AND, in this case operator, which gets the address of something, and the dereferencing, which actually dereferences a pointer. Okay, and in a lot of cases we initialize a pointer with a null or a zero, which means that it points nowhere, basically. Okay, so don't forget that at the end of the day, addresses, which are the values that a pointer can hold, are at the end of the day values, so they can be manipulated, the +1, -1, +2. Okay, and don't forget also that pointers that are typed, which means that a pointer to an integer is different from a pointer to a char. Both of them are addresses, but if I initialize an integer pointer, then the address has to be an address of an integer, and if I initialize or I declare a char pointer, then the address has to be the address of a char. Okay, now we will move on to the new concept of today, okay, which is structures in C, and this is actually a very useful, a very used, and a very famous concept in C. Okay, now structures in C might remind you with objects in Java, but they are different. C is not object oriented. Okay, so it's not even similar to what we can do with classes in Java. Okay, there is a bit of a similarity in some context. Okay, however, it's totally different. Okay, the idea of having structures in C is basically to extend the data types that we have in C. So basically what we will do is we will collect a group of variables together into a structure. Okay, if you remember in Prolog, we used to say that a structure is a complex term. Okay, so this is basically similar to that. It's at the end of the day a value, okay, however it's a structure, it's structured somehow. Okay, it has a collection of specific variables and every variable has a specific type. So it could be that a structure will have different variables with different data types. Okay, so basically what we do is we group pieces of information together. Okay, so for example, a student has a name, has an ID number, has a list of, for example, courses. Okay, so in this case what we will have is we will group different pieces of information together for every student. Okay, and this will make programming easier in this case. Okay, we have two main ways to define a structure in C. This is the first way, and in this case we use the keyword struct, and this keyword we will have to use it, and then you use the name of the structure that you're defining and then the collection of variables. Okay, so let's take this and play with it in our IDE. So in this case you just define the structure. So I'm defining a new structure called card, and it has two variables, a value which is an int and a suit which is a char. Okay, now what I want to do is I want to declare a new variable, and this variable should be a card. Okay, now what you would want to do is you would want to do this card C1, C2. okay, which means that I have two variables, C1 and C2, and they are both cards. Okay, now if you try to compile this, you will face a problem. Okay, why? Because in this case, it's not actually a card, it's a struct card. So what you need to do is you need to add the keyword struct. Okay, once you do this, you will not face the error anymore. Okay, so in this case, you just don't you should not forget to write the keyword struct. What you can do afterwards is you can access the values. So you can say c1.value is equal to, for example, 5, and then c1.suit is equal to, it's a char, so it's equal to a z. Okay, now this also will not cause any issues. Okay, okay, so let's take a look at another example. If you want to have an array of cards, in this case you cannot go and say card, for example, array of 10 elements. Okay, you cannot declare it this way. Okay, if you try to do this, you also get an error. So what you need to do, you need to add the keyword struct. Okay, once you do this, you have declared an array, and this array is of type, or the elements of the array is of type struct card, and the array has 10 elements. Now you can say array of 0 is equal to C1, for example. So in this case, you're assigning the first element of the array to be this card that you just did. Okay, and you will also not face any issues here. So if you go and you decide to print, for example, value, comma, suit, and then you print array 0 dot, in this case, the first one is the decimal, which is the value, comma, array 0 dot suit. Once you compile and you run, you get the value and the suit. Okay, so array 0 by default is of the type struct card. You don't have to do any typecasting, it's there by default. Okay, so this is the first way to define structures in C. Now, as you might have seen, having to write the keyword struct is kind of annoying because it doesn't really add a lot. We know that this is not a built-in type. Okay, so there is a way, or there is another way to define structures that will eliminate the need of you to write struct every time. How do you do this? In this case, what you do is you add the keyword typedef, okay, before struct, and the name is actually written at the end. Okay, so this is another way to define a structure. Okay, the nice thing is now when you declare a new variable of this structure, you don't have to write the keyword struct. So if you go back to the same example, what I did here is I changed the definition of the card to use typedef. Okay, so typedef struct and then card at the end. Okay, so now as you can see here, I removed the keyword struct from this declaration and from the array declaration. If you compile and you run, it still works. Okay, so as you saw in this example, we can have inside the structure an array. Okay, so in this case I can go and I can access the array and assign a value to it. Okay, so in this case you can collect whatever values and whatever variables and data types of these variables could be different. Okay, now with structures we face some issues in a lot of cases, which is we need to have some sort of dynamic structures that will go big or small according to what we need, and we might not actually know what we need while we are writing the code. Similar to, for example, an array. To initialize the array, you need to know how many elements you will have, okay? And this piece of information could be something that you will get from the user. You actually don't know it now. It's an input from the user. It's something that you scan from the user. And for that, we use something that we call the dynamic memory allocation, okay? Now, in addition to dynamic memory allocation, which we will study throughout the rest of the lecture, we also want to combine it with the fact that we would need to define more complex and more interesting structures. Okay, so if you go back to, for example, CS3, okay, you've been doing data structures like linked lists, like trees, and so on. So we want to be able to define something similar to that with C. The problem now is that with C, we do not have the option to have recursive structures, okay? So you cannot have one of the variables of your structure to be of the same type, okay? So if you go here and you try to add, for example, card, next card, okay, and you compile, you will get an error, okay? If you do struct card, next card, and you compile it, you get an error, okay? Now, what we will have to use in this case would be pointers, okay? So I cannot directly use the same data type, but I can use a pointer to it, okay? And the pointer is okay because at the end of the day, the pointer is an address, but I know that it's an address to something that I'm interested in and something of this type that I want to have, okay? Now, before I show you how we do this, I want to show you something that you might find in some resources, which is in a lot of cases when the structures are defined, you will find that the name is written here and there, and they can actually be different names. And this has to do with the name spacing and so on, okay, and the scopes of where to use which name, okay, and we will not go there, it's not of interest to us, okay, but I want you to know that if you see it, it's not wrong, okay, and in this case what you can do is you can have the same name in both fields, okay. Usually what we will have is we will just write it there, okay, but if you see it written there, it's also correct, okay. Now let's move on to how we can define a recursive structure. In this case, what I need to do is I need to have a pointer instead of having a card. So I need to have a pointer to a card, okay. Now the problem is if you do it this way, it will still not work. Why? Because at this point, the complete way the card is defined to be used this way is not done yet. Where will it be done? After the full definition is over, sort of, okay. So this is sort of the idea. We are still defining the card, okay. So in order to be able to use it, I will use it this way, okay. So instead of using card alone, I will use struct card, okay. And the easy way to relate it is just because this is what's so far defined, okay. In order to use the card alone, we have to go there, which is not there yet, okay. So basically, if you do this, now this will work, okay. And now what you can do is you can say that C1 dot and then next card is equal to, my question is, can I say is equal to C2? Now you have to go back and to think, okay. The next card has which data type? Is it a card? You will tell me no, it's not a card, it's actually a pointer to a card. So what we will do here is we will say C1.next card is the address of C2. Now once you compile this, you will not have an issue, okay. So this is sort of linking a card to the next card, which you can use to define, for example, a linked list, okay. Now let's try to do it this way. So I have type def struct, okay, without a name here, and then I go and I try to define a pointer, okay. If you try to do this, you will actually have an issue, okay. You will have a warning is from incompatible pointer type, okay. And this is why, in order to be able to use struct card, okay, I have to have a struct card, okay. So this is sort of the idea. There are a lot of details behind it, and there are different ways to do it. In order even to get rid of the struct that we have here, there are like workarounds that could be done, but we are not interested in that, okay. The important thing for us is for you to know what structures are in general, how to use them, okay, how to link them with pointers, and how to deal with dynamic structures, okay. So this is our focus, okay. The other things are technicalities that will not actually affect the goals that we want you to learn about this paradigm, okay. So for us, we will usually use it that way. We will have type def struct, and then we have the same name here and there, and this way we can use struct card as a pointer in order to link and to sort of have a recursive type. So it's not actually recursive, but it is sort of recursive. Okay, now let's move on to dynamic, in this case, memory allocation. So take a look at what we have here. In this case, we define an array of 10 elements, and we can do it even for integers. I can define an int array with 5 elements. Okay, and once you do this, the memory will be assigned for this array. Okay, and the memory, let's say, size assigned to it has to do with two things: with what is the data type, okay, and how many elements. Okay, so if you think about an array of integers and an array of double, which one will take more space inside the memory, even if both of them have 5 elements? Okay, will it be that the size of this array in memory is equal to the size of this array in memory? Of course not, because this is a double number, which means it's double precision. Okay, if you remember, which means that it takes more bits from the memory. Okay, so at the end of the day, every system and every computing system and every CPU has for every data type its own, or the number of bits, let's say, fixed for it. Okay, so the compiler will sort of use this. Okay, so basically what will happen is once you define an integer array, it will know, for example, an integer, let's assume, takes 32 bits, and you have 5 elements, which means that for this part of the code, I have to reserve a chunk in the memory, a continuous chunk in the memory that has a size of 32 times 5. Okay, in this case, the double can have, for example, 64. So I will reserve a chunk in memory with 64 times 5. Okay, now in C, actually, because as we said, C is not very high level, so it has some low level aspects. So what you can do is you can print the size that every data type takes. So I can say the size of int, and then I print a number, and then I will call a built-in function called size of, and here you can define, or you can actually input any data type that you want to know its size. So let's try it with an int. So in this case, let's just print a new line. In this case, size of int 4. Okay, let's do double. Size of int, because I just wrote int, so if you change it to double, you get size of double 8. Okay, what about a char? Size of char is actually, it's 1. Okay, so in this case, size of is a built-in function, and it actually returns the size of this data type, okay, in bytes. Okay, what you also can do is you can use size of with even the structures that you define. So here I have a student, which basically has only 2 variables, an ID, which is an integer, and the semester, which is an integer. And if you check what's the size of a student, in this case, let me just try it here, student, you get the size is 8. And this number should be logical, because the int takes 4 and the other int takes 4. Okay, however, it will not always be the case that the size of the structure that you get is exactly equal to the summation of the sizes of each of its variables. Okay, so if you get a different value, it's not an error from your compiler or in your code. It's totally normal, because what C does is it tries to do paddings, okay, for the extra, let's say, places, okay, and this is something that's automatically done by the compiler. And this is the nice thing about having a size of, is that you don't have to think of what will happen inside the memory. Okay, you just use the size of, and it will tell you by default what size this structure will take, because the size will differ. If you have, like in this case, different data types, then the order in which you write the data types will make a huge difference in or can make a difference in how the padding is done, and thus how much, in this case, memory will be taken. Okay, so by default we just use the size of. Okay, now let's go to the dynamic memory allocation. In this case, instead of having something like this, where you would know, or the system would know exactly how much memory would be needed, okay, we will go for a case where we want to scan from the user the number of elements that are needed for the array. So in this case, the memory allocation has to be dynamically done at runtime. Okay, and this is something that C allows you to do, okay, to go and to reserve chunks from the memory at runtime. Okay, to do that we will use a function called malloc. Actually, to be able to use it, you have to include this header file. Okay, so in this case what we will go is we will allocate, and let's start with a simple example. Malloc is a function that takes how much memory, how much or how big is the memory chunk you need to reserve. So in this case, let's start simple. I want to reserve a memory chunk for an integer. I don't know, I will not memorize how much the integer will take, because it could be different from one system to another. So I just say I want to allocate as much as an integer needs, size of it. Okay, now what does the malloc return? It returns a general pointer. Okay, they call it a void pointer. Okay, and in this case what we need to have is we need to have an integer pointer. Why? Because we know that we are allocating for an integer. malloc would not know this. Malloc knows that this is how much you need to allocate. This could be for an integer or for 4 characters in a structure. It wouldn't know. Okay, so in this case, this is why the malloc returns a general pointer, and this pointer is actually the pointer to the first address of the allocated chunk. Okay, so if you go and you allocate a chunk of the memory, okay, in this case the chunk could be big or small according to what you supply for the malloc. So let's assume that we allocated these 2 chunks, for example. Then in this case the pointer returned from the malloc will point to this address. Okay, now what we need to do is we need to make sure that this will be compatible, because now we have a problem. This is not an integer pointer. The output of this function is not an integer pointer. So what I will do is I will typecast it. Okay, so this is usually how we will do the memory allocations. You just know how much you need, and then you typecast, and then you have the pointer which points to the first element. Okay, now my question to you is, if I have a char pointer, and this is a general question not related to dynamic allocations. If I have a char pointer and a character pointer, and I increment both, okay, will it be different? Will the output be different? Yes. The result here, or the displacement that will happen here and there, will be different. Why? Because the integer takes more place in the memory. So the next integer, okay, the difference between 2 consecutive integers is more than the difference between 2 consecutive characters. Okay, because the integer is larger, it takes more memory. Okay, so this is why when we have a pointer and we increment the pointer, we say that it points to the next cell, but according to the type, to the next available, for example, in this case, integer, if it's an integer pointer, okay, to the next pointer. So it will actually add to it as much as the size of this data type is. Okay, so this is something that you might also face. Okay, so it's good that you know where it comes from. Now, what if I want to allocate for an array of 5, in this case, integers? Okay, in this case, the function is the same. I will allocate, but instead of allocating for 1 integer, I will allocate for 5. Okay, and now the p will actually be the pointer to the first element of the array. And this is why, if you want to assign an element to the first element of the array, you can dereference the p and say that the value is 6. The second element, if you remember what I just said, we can do it simply by saying p plus 1. So p plus 1, okay, is the address of the next integer, okay, and then you dereference it and you assign whatever value you need, and so on. Okay, so that way you are actually allocating some space, and you can go and you can assign the values you need to. Okay, now the most important thing you need to know now is whenever you actually, so we have here a problem. Let's fix that. I have a missing bracket there. So whenever you use the malloc or any other dynamic allocation function and you allocate a chunk of memory, this chunk is reserved by you to your use in the program. Okay, and this is why you have to make sure that you free it. Okay, because otherwise you can face big problems. Okay, and messing up with the memory is not an easy task. Okay, so in this case, never forget to free. Okay, after you're done. So what will I free? I will free and I will send to the free function, okay, the pointer of the first address of the memory chunk that was reserved. Okay, and this is why pointers and dynamic memory allocations are very closely related. Okay, so now you might have an idea of what we will do next. Now, instead of having this 5, I can replace it with an n, such that the n is a number that I will scan from the user. So in this case, I can say int n, and then I scan f for the n and n. Okay, and you use the n in order to allocate the memory, and then what you can do is you can start to assign values. So according to the size, okay, every time you can go and you can do this asterisk p plus I is equal to, and then you can just have the I. Okay, so what I have here is I have an array with a size n, and then every element of the array will have a value equal to its index. Okay, what we can do next is we can go and we can just print. So I print f, and then I print this. Okay, so let's see what we get. So I will enter, for example, 7. So I have 0, 1, 2, 3, 4, 5, 6, which is correct. Okay, so in this case, if you want to have it in different lines, you can just add the new line. I have 7, I have 0, 1, 2, 3, 4, 5, 6. Okay, now what you need to make sure of is that what you free is actually the correct thing. Okay, so this is why, as you can see, I did not mess up with my p. So in this case, my p is the same. I just add, okay, the I, but the p itself, I did not change it. I did not assign a new value into the p. What if I will assign a new value to the p? Then in this case, I need to save the old address, okay, in a temporary variable in order to be able to free it afterwards. Okay, so now let's combine things together and see an example where we will have to use different, let's say, concepts. Okay, so here we're trying to define a tree. Okay, and it's a binary tree, so every tree node, okay, basically has an integer value, which is the data, and it has a left and a right tree. And because we cannot have, in this case, the recursive structures, as we said, we will use pointers. Okay, so this is basically the first part. Okay, now what we usually do is we usually add such a function, okay, which is a function that would create a new tree. So as you can see, this is actually a way to make things dynamic, because I don't want to define things or to define my tree in the main method or in the main function. It could depend, and in many of the cases it will depend on inputs from users, and this is why we define functions that dynamically build the trees or build the values inside my data structures. Okay, so for example, I would not know how much the linked list is or how big the tree is. Okay, but as I take input from the user and as I process my data, I will keep on adding things. Okay, and this is why it's closely linked to actually dynamic memory allocations. So let's take a look at different ways in which we can do the create tree node. Okay, now this is one way to go. Tree node cn is equal to, or without is equal to, cn, and then cn dot data is equal to the input data, so data, and in this case cn dot left is equal to null, and cn dot right is equal to null. And what do I return? I return the new cn. Okay, Now, here we have an issue. Why? Because in this case, what you return, okay, is not a Java object. We don't have a Java object. This is not an object. This is just a value, okay, which is, it happens to be a structure or a structured value, which happens to mean that it just combines different things together. But at the end of the day, it's a value. And if you remember, what is created inside the functions is deleted, is removed automatically from the memory once the function is over. So what will happen is, this will go to the memory, okay, let me try to draw with you, okay, and it will, and it will create the tree node, whatever it will do. Let's assume this is my tree node. It will assign the data, it will assign the left and the right, okay. However, what it will do is it will return a copy of this, okay. However, this will actually be removed, okay. So if you try to point to it afterwards, you will face a problem, okay. And this is why what we need to do is we need to make sure that we do not return a copy of this. We actually return where this is, okay. And we need to make sure that this remains there even after the function is executed and done, okay. And this is why we will use the dynamic memory allocations, because we will know that this memory chunk will be reserved to us unless we clear it, okay. And this is why, let's move back, we will do it with the malloc. So what I do is I allocate as much as I need for a tree node, okay. And then what does it return? It returns a pointer, which I will typecast into a tree node pointer, and then I will access the data, the left, the right, and set everything. And what do I return? I return a pointer. So I return a copy of the address, but at the end of the day, I have the address of this chunk that I allocated, which will be there with the data that I need, okay, which means I can use it afterwards correctly, okay. Now, if you want to go and you want to delete a tree node, what do you need to do? You will need to free the memory, basically, okay. But remember, a tree node is not only this part of the memory, it's linked to its left and right children. So what you need to do is you recursively need to free the left and the right, and then you need to go and free this tree node. So basically what you go and check if the pointer is null, if the tree node you're trying to free is actually not there anymore, then you just return. Otherwise you delete the right, okay. So you delete the tree starting from the right, and you delete the tree starting from this left node, and then you free the pointer, okay. So this is basically the idea, okay. So the most important thing is for you to understand how to link pointers with structures and use them, okay. It's the same concept repeated. And the basic new thing is the malloc, which allows you to allocate memory from or to allocate memory as much as you need, okay. However, never forget to free the memory that you allocate. malloc is not the only function that is available for dynamic memory allocations. There is also the calloc, okay, as another example. However, this is the one that we are interested in, and it actually is more than enough. So now in the tutorial, you will go for more examples of using structures and dynamic allocations, okay. Please let us know if you have any questions or if anything is not clear. Thank you so much. Stay safe. Bye.